So previously ended this genetic algorithm up to this slide, and now we are going to see that another example of genetic algorithm, but we are going to take an idea. So just a recap, what is genetic algorithm? Because otherwise, if you have not attended the previous class, then you will not understand what is happening there in the slides where you have that chess game. So this is the genetic algorithm taking population and fitness function for calculating the fitness of the members. This is the variable population, and then the gain again the same things. Population is something initially you will have some individuals or members in it, some strings in it, and fitness function. This is a formula to calculate the fitness of the members which would be here in this population. We have a repeat until loop, and here in this repeat until loop, initially this new population is another variable which is initially empty. Then we have this loop starting from 1 to size of the population, and then here we are randomly selecting two members from this population, and then we are applying reproduce function over it. Reproduce is what? Reproduce is a function which is for applying the recombination process. Through this reproduce function, you are applying crossover operation of the genetic algorithm over these two parents. What will happen? It will cut down the tails of these two parents and it will swap the tails. Okay. So, and then a new child will be produced that you are going to store here. And then if you have some small value of probability, then you can apply the mutation over this child, and then you will get a new version of that child. Or if you don't have the probability, then you will do what? You will add this child directly into this new population variable. And in this way, you will go on. You will select each time two members from the population and you will apply these operations over them. And you will go on until this until the members of the populations will be ended. And then this loop will be ended, and then you will come here on this statement, and here in this statement you are doing what? You are putting this new population, the new population in which you have the children. You are putting this new population again into the population variable, which is this one, and then you will come here and you will check this condition that in the population you have individuals. So then you will check that in this population you have some individual which is fit enough. If you have set a condition that if you will have some member which has an 80% of fitness, and if that person is available in the population, you will go out from this loop. Or another condition is the enough time has elapsed. And if you have set a condition about timing that you will run this loop for 2 hours, and if those 2 hours are ended, now you are going to go out of this loop. So after the ending of this loop, then you will come here at this return statement, and it will return simply the best individual in the population. And how you can calculate this best individual? Through this fitness function that you have here. You are calculating the fitness of the members through this formula. Anyhow, now let's start properly from this example. So we have seen these 8 queen problems in previous COs, and all are the solutions, and all are the different solutions where 8 queens are placed on the chessboard and no any queen is attacking another. So now, for example, if you will see this first case, so this is no any queen is attacking any other queen here. This is one solution, and we can represent that solution with this string. What it means, if you will start from the 0, 1, 2, 3, 4, 5, and so on, 6 and 7, then the first position of this queen in the first column is 1, okay, is 1, starting from 0. And then here in the second column, the position of this queen is sixth column, which is written here. And similarly here, the second column. And similarly, the position of this is fifth column. And in this way, you can see you are writing all the positions here of each column. And then you have some string of digits, huh? You have some sequence of digits or string of digits. Similarly, for this solution, you can represent all the positions with this sequence or string of digits. And similarly, for that one, you have this string. So you have strings for which are representing all the positions. Now, if I will give you any random position, not the solution, okay? I will give you any random positions, not the positions with this solution. I will give you some population in which you will have individuals, which are maybe which are the individuals of an individual can be a state of different chessboards, okay? Not with the solution string, not with the solution string. Maybe one solution string is available somewhere in the population. And then you can do what? Then you can apply the genetic algorithm over this population to get the solution board for this problem. That genetic algorithm will automatically find the solution if you will give initially in the population the individual boards with different positions, not with the solution position. Even if you will not give the boards with without solution positions, it will find the solution automatically. How? Let's see that. The idea is that if you have one position this, which is not a solution, and another position this, which is not a solution for this one, this is for this board. So if you have these two strings available, you have many strings available in the population, but you are selecting two each time. And suppose you selected these two uh, during the execution of the genetic algorithm, then what? You after the selection of these two boards, then you will select the crossover point. And suppose the crossover point is after the third column, after the third column. In both the boards, the crossover point is what? After the third column. Now you have to do what? You will swap this tail here and you will swap this tail here in this board. And then this, so that's why you are seeing only here you have a child which is produced after swapping the tails of these two boards. And here, this first yellow area is depicted here. And then this tail is depicted here. And then you have a new string, new child. Here only one child is displayed. You can have another child by this black and white area, okay? By black and white area, you have another child. And then the new children will be produced, and then you can put again these new children in the population, and again then you will select again the two children from the population. Then you will apply again the crossover operation over it, and then you will put again into it. And in this way, this string will remain changing each time. And if you will finally reach on these strings which are depicted here, these are the solutions, huh? If your algorithm will reach on any of these strings, then you can do what? You can make an exit from that algorithm. And in this way, genetic algorithm can find the solution by itself. Hmm? Hmm.
Every map of those should have the cross on them, or I am the one who should.
This crossover point, this point you can select randomly by the machine. Okay, you were not present in the lecture when we studied this algorithm actually. So I explained here you can select, we studied all these things, that how we can select the crossover point, how we can select, for example, here mutation, we are selecting this mutation with the probability. And I explained here what is the meaning of this probability. Here I'm explaining in these previous things what is the meaning of the small probability. Okay. And as far as the crossover point, if you will come here you are selecting randomly, random number from 1 to n. So 1 to n means the total length of the string, and you are selecting randomly. And so anyhow, now another example. It's the same example, but now it's a little bit complete picture. Here you have some different sequences or strings. You can consider the same strings that you already experienced here in this example. And then you have the fitness values for these members. So this is the fitness value for this one, and this is the fitness value for this number 2. Number 3, it has 20 fitness value. Number 4 has 11 fitness value. If you will sum up all these values, and then if you will do 24 divided by that sum and multiplied by 100, you will have the percentage, huh? You will have the percentage. What percentage of this 24 out of that total sum? Similarly, you will have these values calculated through these values. So this is the percentage of fitness. Now, in this example, you are selecting the, uh, for example, now the next step is selection of parents. And here, these two values are close to each other, 31 and 29. These percentages are close to each other. So that's why you are selecting this and also this one. You are selecting these two members from this population for the crossover operation. For the crossover operation. So, and here you are writing these strings as it is here. And then in the next step, you are selecting the crossover point. After selection of this crossover point, then you are swapping the tails. You are moving this tail to here, and then you are moving this tail to here, which you can see here in the next step. So here in this phase, you are making pairs, you are making partners. Similarly, here we have this 26 and we have this 40. In this example particularly, we are ignoring the 14 because ignoring is very much low as compared to these values. And we are taking these 29 and 26. So you are taking top 3, you can say, okay? Top 3. Because the last one has quite low value as compared to these 3 values. So that's why we are ignoring in this example only. In this example only. But there are different methods for selection. We have studied 2 methods already. One is a lee-test, other is, we have studied these methods, roulette wheel selection, a lee-test method. A lee-test is something you have to select top 50, top 30, top 40. And roulette wheel is something with the percentage. With the percentage that individual is taking from that wheel. And here percentage is not working. Here something like roulette wheel is working. Or you can say percentage is working. Okay. Percentage, but the percentage is like that. You are selecting top 3. You are not selecting all. So anyhow, so if this is the crossover point, then you are swapping the tails. So 327 and then 4552, which is written here, and similarly 247, and the tail of this one is mentioned here. So now this is the step for the crossover. After applying this crossover, you have now this situation. And here we are selecting, I said you, I said this already that here we are selecting, we are ignoring this 14 because this is a quite low percentage as compared to these three values. And then these two are becoming the partners here. And then this is the crossover point, and then you are swapping these tails and you are getting these situations here. And in the last, we are applying mutation. Mutations mean changing only one position. Either it is a bit string, you can change only one bit. Either it is a sequence of digits like that, you can change only one digit. And here, 327485552, we are selecting this one and we are changing this digit to any other digit which is available from 0 to 9, which is available from 0 to 9. Here we are not changing anything, and here we are applying again the mutation because we are changing it only at one position. This is called mutation when you are changing one position. So here we are selecting this one, 7, and we are changing it to 2. Similarly, here we are selecting 1 and we are changing it to 7. This is the mutation process. So So when you perform something like that and when you store the things like that, it is the example here that you have seen here. It is the variant of the stochastic local beam search. There is another algorithm which has the name local beam search, stochastic local beam search. Its execution is again like similarly as we have explained here. Its execution is same. It will generate the next neighbors from the pairs of the states. And you will encode those pairs like strings, as you can see the strings here. So this example is an example like a stochastic local beam search. Now we are moving next. These are the applications of the genetic algorithms. You can read it by yourself. So you can use this genetic algorithm by solving the problem of traveling salesman person or vehicle routing or routing problem, navigation app, financial markets, you can use it, manufacturing system in industries where you are manufacturing different products, mechanical engineering design. So you can read this, that you can apply this genetic algorithm in all these areas. And in this way, the CO 3 is finished. And now we are going to start CO4. So what is the statement of this CO4? If you will see over here, this is about constraint, investigate constraint satisfaction for a given set of problems. And if you will see the book, in the book, it is constraint satisfaction problems, okay? Constraint satisfaction and problems. This is the name of that chapter. Constraint normally means condition. So you have to satisfy the condition, constraint satisfaction, for some problems, huh? For some problem. So problem will be given to you, and then you have to analyze the problem, and then you have to assign values to the variables, and you will keep on assigning these values until you reach at the final solution. We will see this. So now here you can see constraint satisfaction problem. What are you doing with your mobile phones, huh? Don't do that. I already said many times that during the class timing, do not use the mobile phones. So constraint satisfaction problem. So we can shortly say it CSP. What is this? It is okay, it is a problem. But in this problem, we will look first for what are the variables, huh? And if you will find the set of variables, you will find the variables. If it is more than one, then I am calling it set of variables. So in each problem, you will find the variables first. And when you will find the variable, then you will start assigning these variables the values. Okay. And you will keep on assigning the each variable the values. Those values that you will assign to these variables, you will assign only by looking at some conditions, by looking at some constraints. And if those constraints are okay, and if those constraints are satisfying, then you are going to assign the value, otherwise not. And in this way, you will keep going on until you reach at the last assignment. Last assignment means until you reach at the last stage where you assign the last value to the last variable. And then the problem will be solved. And this situation, so this situation is called CSP. This situation is called constraint satisfaction problem. Okay, now open it again. Now we are going to open our problems. Generally. So if some problem will be given to us, it will consist of three things, or you have to identify three things. What is the first thing? The first thing, you have to find the X. What is that? Set of variables. What are the variables in that problem? You have to find it. You have to identify it. And here we are just writing generally that x1, x2, x3 up to xn. These would be your variables, huh? In that problem. And then you have to identify or find the set D. And what is D? D would be the domain. That D would be the set of domains or the set of values, you can say. Okay. And we are representing those with D1, D2, Dn. You can also represent it with V1, V2, V3, and so on, Vn for values. These are just, and then the third thing that you have to identify from that problem is the C, set of constraints, are the set of conditions. What are the given conditions in that problem that you have to follow, that you have to check during assignment? So you have to identify these things, three things. Let's see the example now. This is an example of a map coloring. Here we have a map of Australia, huh? And these are the states mentioned here. So Western Australia, Northern Territories, South Australia, Queensland, New South Wales, Victoria, and Tasmania separately. These are the states. So the problem is that this map will be given to you, and you have to assign colors to this map, but you have only three colors. Okay, red, green, blue, for example. So this red, green, blue. So when this problem is given to you, then this red, green, blue is what? It is your set of values, huh? That you have to assign. That you have to assign to these different states. That you have to assign to these different pieces of the map. So these red, green, blue is the set of values. But here you have to assign these values to where? On these states. For example, this is one state. This is another state. This is another state. This is another state. So these states to which you have to assign the colors, these states are called what? According to our understanding. Yeah. According to this previous understanding. So then these states are called what? Variables. Okay. Because you have to assign values to these variables. So now these are the variables. I said to you, whenever some problem will be given to you, you have to identify three things: set of variables, set of values, and the set of constraints. Yeah, values, you can say set of domains or set of values, it's the same thing. So here it is not mentioned what is the problem. Question is not, I am saying, I am explaining the question, okay? I will give you this question or some other question theoretically in a paragraph. You have to identify variables by yourself, values by yourself, and then you have to find the solution. So in this problem, my variable set is okay. I am calling it X, and it is containing what? WA. WA means Western Australia. This one. NT Northern Territory. Q Queensland. This one, huh? NSW New South Wales, Victoria, South Australia, and Tasmania. So these are the variables. And the set of values or the set of domain is what? Red, green, blue. Three colors that you have to assign. You have to assign these colors here in the map, but what is constraint? What is C? No neighbor or no neighbors here in this map will have the same color. So all neighbors here in this map will have different color. And you have only three colors to assign, red, green, blue. So if you assign G here, this cannot be G here also. This cannot be G here also because this is neighbor. So you can represent this graph by this constraint graph, which is representing what? Which is representing neighborhood. Y is a neighbor of, due to this line, you can say Y is a neighbor of NT from this map. Y is also the neighbor of SA. SA is the neighbor of NT. NT is the neighbor of Q. So all these lines which are drawn here representing neighborhood, which you have seen from here. This is the neighbor of these different, this is the neighbor, huh? And all these lines are here. And then these neighbors, these are also neighbors, which are depicted here. So this is a neighborhood graph, you can say. If you are not, and this concept, finding the neighborhood, is very much essential because only then you can assign the red, green, blue color to this problem properly by looking at the conditions. So now the constraint is what? Neighboring regions or neighbors must have distinct color. Distinct mean different color. Okay. Now you can go on by any direction. You can go on by any direction. So you can start, okay, I will assign it green, and then I will assign it red. Then I can assign it maybe the blue here, huh? And then I can assign green, then red, then green, and then here you can assign any because it is not the neighbor of anything. So this is one solution then. So this is one solution which you are seeing here. So many solutions are possible, but that is one solution. So that one solution is how you can write it in theoretically. So Y is equal to red, NT is equal to green, Q is equal to red, NSW is equal to green. And if if I will depict this thing graphically, then this would be the picture, huh? So this is red, green, or something like that. And here now in this solution, every neighbor has a different color, and no any connected regions or no any joined regions have the same color. So this is a simple example of this constraint satisfaction problem. This is simple example, so that's why it is looking easy. But when the problem is a little bit complex, then you have to uh, see different things. So what is the advantage of this CSP? So the advantage is, if you will not follow this CSP, then you will compute each and everything. You will see all the possible options. Maybe, for example, for this problem, if you, here you have how many states? 1, 2, 3, 4, 5, 6, 7. So then you can say 2 raised power 7 computations for this one. Maybe you have to check. But but if you will follow why, so sorry, here the colors are three, okay? Colors are three colors and 7 states. Hmm? So total possibilities is this that you have to check for finding the solution for that. But if you know how to solve a CSP problem, then this number of computation will be reduced. Okay, will be reduced. You will not check all the possibilities. And this example is given here. And it is being said here that suppose when S is blue, when you made this state blue, and now for example, here, for example, you have given this state the color blue, and now you have to give color to these states. And how many these are? 5. Leave this. This is a separate. Leave it for a moment, huh? Because I am following these 4 lines. In these 4 lines, this is ignored. Hmm? So you have the blue color here. And now the blue color is assigned. Now the blue color is assigned. And now you have, what is the set of the colors? 3. So you have 3 for this, 3 for this, 3 for this, 3 for this, 3 for this. So then what? How much options you have here now? 3 raised power 5. 3 is the number of colors, 5 is the number of states. And you have 243, huh? So you have to check 243 options there if you will not follow CSP. If you will not follow CSP approach. But if you know what is the CSP approach, then this blue color, which is the neighbor of all these states, and according to this CSP, I cannot assign the same color. So which means I cannot assign the blue color to these states, which are the neighbors. So then this option is now gone. Okay, you don't have to check it. Okay, you don't have to check. This is what CSP is giving you this knowledge. You don't have to check like 3 raised power 5. 3 is the number of colors. No. For all these statements, now you only have 2 colors, not not 3. And then you can check something like that. And if you will do this, and it would be 2 raised by 5, only 32 assignments. So you reduced your work from this 243 to 32 only. This is the advantage of CSP approach. This is the advantage of CSP approach. Okay, now here, uh, this is shortly written here for 2 different situations. You are writing some mathematical equation. Here here in this case, we are calling that sometime in life, we have to give precedence to something more as compared to other thing. Precedence means, I don't know, maybe Fokia Filarabi. Okay, so sometime again in your real life, sometime you have to give more preference to something as compared to other thing. This is so, and if you have a situation, then you are following the precedence constraints. You have a condition of precedence in your mind that you have to follow. For example, here, if you have 2 tasks, task T1 and task T2, and the duration of task 1 is D1. Duration. The task T1 takes D1 time to complete. Okay, that is what the duration means. So you have 2 tasks, task T1 and T2, and the information is task T1 will execute first. And the time duration for the task T1 is what? D1. And now, if the question is write it in a mathematical way, then this would be the mathematical way. T1, which is a task 1, plus D1, which is the duration. And this will execute first, then the T2. So how you can write less than or equal to T2? So it will execute. When it will be finished, only then T2 can start. So that's why equal to is mentioned. Or if there is a gap, okay, then less than. So this is mathematical representation of this precedence constraints. You can represent these constraints in a mathematical way. Hmm? Now, another example. What is disjunctive constraints? Disjunction operation, you already know. Huh? Conjunction, disjunction. Huh? Conjunction is and, disjunction is or. So now in this example, disjunction. So disjunction is involved. And for this, in this example, we are saying that there are two axles, axle F and axle B of a vehicle, huh? Of a car or of a vehicle. There are two axles, front axle, rear axle, on which you have the wheels, huh? So there are two axles, axle F and axle B. These two axles you have to install, huh? You have to install in the vehicle. And the condition is they must not overlap. Either axle 1 you can install first, either axle B you can install first, but you cannot start it at the same time. This is information given here. And one axle can take how much time? You can say 10 hours or 10 minutes or whatever. Then how you can write this precedence? Sorry, then how it is precedence also. Then how you can write this uh, constraints mathematically? So this is the equation then. XLF plus 10, it is the time. And then it is less than or equal to XLB, or I'm using the word or, okay. Or you can write the other way, huh? So by writing both the way, then this equation will complete. XLB plus 10 is the time less than or equal to F. So so now we are moving towards some topic in which the constraints are involved, okay? For example, here, I don't know if this will complete within the time or not. I have the time up to what? 10:45 maybe, huh? So this is crypt arithmetic problem. I can shortly call it CAP. What is that problem? Here you will be given two strings, place plus val. You have to add these two strings and the solution would be better. So now so these two strings would be given to you. You have to add them and then you will get some another string. How you might be thinking that how this is equal to this better. This is not easy. Okay, this is cryptography. Okay, this is called cryptography. You will encode some information into this problem and then you will solve that problem. And after that, so something is hidden here. Okay, something is encrypted here, which you need to understand, and only then you can understand how these two strings you are adding and you are getting this string better. So actually behind this, the digits are working. For example, these are the digits behind this play, and these are the digits behind this well. And when you are adding those digits, you are getting this one, which is equal to this better, which is equal to this better. So actually behind this puzzle, digits are working. So if you have some kind of a puzzle like that, then you have to do what? You have to convert all these individual letters into digits, into unique digits. You have to convert. You have to find what is the digit for B, what is the digit for L, what is the digit for A. And whatever the digit is for A is A, for example, 6. And if you have A again, and then 6 would be again here, okay? You don't have to take another digit for the A again. No. Each letter will have unique digit. Each letter will have unique digit. So now we are moving far next, and here we have an example. Find the solution for the send plus more is equal to money. Now these are the strings given to you. We have to find the solution. Where each, so this is the question, where each unique character, so here we have the characters or letters, where each unique character must be replaced with a unique digit. So you have to replace them with a unique digit from 0 to 9. 0 to 9 and then 10 digits, huh? And the number so formed cannot start with 0. And we are saying that when you will add them, then you will get some number, and that number cannot start with 0 from the left to right. From the left side, there's no possibility of 0 there, okay? This is what this condition is saying. How can we find the solution? But before finding the solution, let's, how many total computations that you have to do for finding the solutions? 10. 10 is the number of digits. 8. 8 is the number of letters here. SEND. If you will count them, it is 8. 2. 2 is the number of carry. When you will add this with that, you will have some answer, and carry is going next. So 2 is that carry. And 4 are the carries, and the value of the carry is what? Either 0 or 1. Okay, either 0 or 1. Either 0 or 1 in this case. So, and when you will compute it, the total computation would be something like that. Even I cannot say what it is, huh? It is a long string. Okay, it is a long string. So this is the total number of computation that you have to look into for finding the solution for this problem. What are these values I mentioned here? 10 digits, 8 letters, 2 carry digits, and 2 carry digits, which are 0 and 1, which will, when you will add these two, add these two, then 0 or 1 will go to the next column for addition as a carry. And 4 carries are involved. How? If you will see here, we are adding 2 strings and like that. And these are the carries, A, B, C. We are representing it with letters. When you will add this D and E, you will have some answer, but maybe carry, either it will be 0 or 1, it will go to the next column for addition. So this is one column, this is another column, this is another column that you have to add, huh? And then the carry. So I can now, so if you will add these two things, then this is the picture. And here we can make equations. D plus E is equal to 10A plus Y. This is the Y here. And this 10A, A is the carry, which is going next. So this is now the equation for adding this column. And similarly for this column, A plus N plus R, where it is? Here it is. A plus N plus R is equal to 10B. B is the carry, and 10 will go next. Huh? It can be 30, it can be 40. So that's why 10 multiplied by carry. Huh? Okay. And the E. This is the, if you will add this is the mathematical equation for that addition. And here similarly for addition of this column, this is the mathematical equation for this. Similarly for this fourth column, this C plus S plus M is equal to 10M. M is this one, and plus O. So these are the 4 equations possible for if you want to add this thing here. We are moving slowly towards the solution. I will start it inshallah in the next lecture because it will take time, and but at least but I will start from here, okay? I will not start from the very much beginning. No, I will start from this equations. And I have to write that this is section 7019. Amali or Nadari, but this is the section.